Okay, welcome to the second lecture of this afternoon. It's a joint lecture. I will try to pronounce the names the best I can. So, Wojciech Kucharz and Krzysztof Kurdyka. And they will they will enlighten us about what regulous functions are. Welcome.
Thanks a lot. It's of course a great honor for us to give this lecture. Our aim is to present some recent progress in some aspects of real algebraic geometry. As you probably know, real algebraic geometry differs from the complex algebraic geometry essentially in many aspects. In fact, well, for me, complex algebraic geometry is somehow perfect, too perfect to fit to the real world. So I sometimes call it utopia. And by the way, Alicia has written an article in the Mathematical Intelligencer, which you got here, about application of real algebraic geometry in medicine, for instance. Okay, so first of all, I give an example, classical example, which exhibit this difference between complex and real algebraic set. So this set is called Cartan's umbrella. It consists of two pieces. It is a real algebraic irreducible set. However, you see two rigid parts. One part is the close of this surface, and the second is the line. So, using language of Zariski topology, you cannot distinguish these parts, and despite that you see that they should be somehow differently, they should be rigid in some analytic sense. So indeed, this I will explain immediately, but first just I will give you content and motivations of our talk. So first part, more historical, is about searching for real analogs of the complex utopia, that is the complex perfect situation. There are two notions which will play a crucial role: arc-symmetric sets, arc-analytic function. The second part is, say, the main part of new recent result, in which we describe real phenomena not existing in the complex world. This will be notion of regulous function. Regulous function is a continuous rational function, but with some special additional properties. And finally, how to apply this regulous function for approximating of function and for a regulus vector bundle. A new theory of vector bundles. So, as I promised, I immediately explain how to distinguish this part of Cartan's umbrella. So this is a notion of arc-symmetric set, which I introduced already 30 years ago. And this set is arc-symmetric. It's a subset of Rn if it has the following property. For every analytic arc with values in Rn, with image of left-hand side of this arc in E, we have also that the whole arc is in E. So in other words, you cannot escape from this set along analytic arcs. And here, when I come back to this Cartan umbrella, imagine that you stay for some moment in this cloud with along analytic curve. Then you can imagine that it's not possible to enter and to stay in this stick, in this line. Okay. So in most cases, we will assume that our set is at least semi-algebraic, because of course, without this assumption, also you may have some pathological example, like even Cantor set is also arc-symmetric, if you like. So what is algebraic sets are of course arc-symmetric, and even connected component of algebraic sets are arc-symmetric. And I proved the following theorem, that the semi-algebraic subsets of Rn are precisely the closed sets of a Noetherian topology called AR, Noetherian topology on Rn, and this topology is finer than the Zariski topology. And here, as you have already seen, this cloth of the Cartan umbrella is arc-symmetric semi-algebraic, but it is not analytic at the origin. So this topology is indeed stronger than Zariski topology. Once we have Noetherian topology, we can consider irreducible sets. We have the decomposition of arc-symmetric semi-algebraic set into irreducible components. And these irreducible components can be characterized as follows. So let E be an arc-symmetric set, semi-algebraic, of Rn, and X an algebraic set which contains E and has the same dimension. So think that X is simply a Zariski closure of E. And if we take by a resolution of singularities of X, then there exists a unique connected component of E tilde, which such that the image of this component is the Euclidean closure of the regular part of our E. Regular part are the set of points at which our set is analytic submanifold of the same dimension as the set. So of course, you see that this is a subset of E, but in general it is not equal to E. But at least it fills a full dimensional part of our set E. And with this theorem, I could find a relation to a notion introduced by John Nash in his famous paper from 1952. So Nash proposed to consider the following condition. So for X, a real algebraic subset of Rn, a subset S is called a sheet of X if it is connected by analytic arcs, so any 2 points can be joined by analytic arc in S. It is maximal for this property and has non-empty interior. When you think about the complex situation, in fact, the sheets of Nash are exactly irreducible components of algebraic set, complex algebraic set. So this I discovered only yesterday. But anyway, so Nash asked whether there are finitely many of these sheets, and the answer was yes. Each sheet is a semi-algebraic and Euclidean closed, and X is a union of its sheets. However, these sheets, they correspond somehow to my arc-symmetric sets, but intersection of 2 sheets of an algebraic set is not necessarily a sheet. So that's why this notion was not so useful somehow, but gives you idea about this geometric approach to irreducibility in the real situation. There is another notion which I also introduced in the same time. It's a notion of arc-analytic function. This arc-analytic function is also, as you can imagine, defined in the following way. We start with the set X, which here you may say it's already R-closed, arc-symmetric, and we consider map. So map is said to be arc-analytic, AA for short, if when we compose this map with any analytic arc, then the composition is analytic. So you see they have the same rigidity property as analytic function, of course, and without any extra assumption, of course, and you may obtain pathological examples which were found in 90s, even non-continuous function. But when we stay in the world of semi-algebraic functions, means the graph is semi-algebraic, then you see that we have this property that any arc-analytic semi-algebraic function is continuous for Euclidean topology. And meanwhile, I mentioned this example, which will appear in our talk at some point. A rational function, which is arc-analytic of class Ck, but not of class Ck plus 1. Yes, and notice that there are arc-analytic semi-algebraic functions which are not semi-algebraic, and for instance, this function square root of x4 plus y4. So now about the properties. I already mentioned first property, but however the ring of the semi-algebraic arc-analytic function on it is not Noetherian. If dimension x is at least 2, but then the ascending chain of prime ideals is stationary. So there is kind of Noetherianity for spectra. And finally, Nullstellen's that holds in this ring as in the complex case. So somehow we were able to discover or to find the property of Nullstellen that in the complex as in the complex case, but in this real situation. Of course, Nullstellen that doesn't hold in the standard way for real polynomials. Okay. And now I would like to spend more time with this slide. So in late 70s and beginning of 80s, Cezar Kuo. Yes, but then this is strange for me to looking down. I prefer to looking up. Okay, so Cezar Kuo introduced notion of Blow-analytic functions. So Blow-analytic functions, as you see, these are functions which became analytic when you compose it with the pi, which is well, in some depends on context, but here it is a composite of finite sequence of blow-ups with smooth centers, Zariski closed centers. If you obtain a Nash function by this composition, then these functions are called Blow-Nash. These Blow-analytic functions were introduced as a tool to define a good equivalence relation for germs of analytic function. And Kuo proved that, in fact, when you have analytic family of analytic functions with isolated singularities, that with this definition of equivalence by like a right equivalence with Blow-analytic homomorphism, you don't have a moduli. So this was the motivation to introduce this notion of Blow-analytic. And when in the beginning, already in 80s, I immediately thought that this Blow-analytic function of Kuo, there should be exactly the same as arc-analytic function, but with extra assumption like semi-algebraic graph. And this was confirmed in a paper published by Birson and Milman 91, that when we consider algebraic case, so it means X semi-algebraic set, semi-algebraic function f on this X is arc-analytic and only if it is Blow-Nash. However, the general case is still somehow open. There were some results, partial results in the same paper of Birson and Milman, but some kind of weaker version, which I don't have time to explain. So I believe that this conjecture is really subtle, and it's an interplay between sub-analyticity and this arc-analyticity is really a delicate point. So this conjecture is true in dimension 2, but not already dimension 3 is difficult. Okay. Okay, so now this is end of the historical part, too long, probably. And now I want to recall you some basic definitions which will be necessary for what follows. We consider algebraic set in Rn a function f on W which is a subset of x. We say f is regular at point x from W. If there are two polynomials pq such that q is non-zero at x, and f can be written as p over q in the complement of zeros of q. Function is regular if it is regular at each point of W. If we have a rational function, then it determines a regular function R on X and except poles of R. So this is, of course, well, this is obvious statement. Pole stands for polar set of R. And now the main definitions. Again, we have algebraic set, f function defined on a subset of this set called W. We take Y, this Zariski closure of Y, of W in X, and we say that for this given f, a rational function R on Y is a rational representation of f if there exists a Zariski open dense subset Y0, which is in Y except poles of R, and f is equal to R on this Y0 intersect with W. Now, two following conditions are equivalent. First, that when we restrict f to intersection of W with any algebraic subset Z of X, we should obtain a function which has a rational representation. One condition. And the second states that we can find a kind of filtration, decreasing sequence of algebraic sets, such that on difference of these sets, our function restricted to W is regular. And so the definition of regulous function, it is a continuous function which satisfies condition 1 or condition 2. This name will be explained by Wojciech later, but in literature there are also two other names for the same category of function. First is hereditary rational, which was proposed by Janos Kolar, and also the second condition was in our joint work with Wojciech. And now, important example due to Janos Kolar is the following. It was very important for the beginning of this story of regulus function in general context. So let S be a surface defined by this equation. This is a real analytic submanifold of R3. And F is a function on S just depending on the one variable. It's a cubic root of 1 plus Z square. And so our S is analytically smooth, but not algebraically. So it has a singular part, it is Z-axis. And when we consider f restricted to s minus z-axis, this we can easily check that this function is, of course, this is continuous because everywhere continuous is a restriction of a continuous function. It has rational representation because we have this f equal x over y. but it is not a regulus function because a restriction to z-axis does not have rational representation, because this is this function 1 plus z square and cubic root from this. And the next theorem is due to Janusz Kolar and Krzysztof Nowak, explains that when we consider X smooth algebraic set, f function defined on a algebraic subset W, then the following conditions are equivalent. F is regulus, and this is equivalent that F is a restriction of F tilde, and this F tilde is defined on X smooth and is continuous with rational representation. So this very short statement has deep meaning, because when you consider X equal W, it states that to be regulus, it's enough to be continuous with rational representation. On the other hand, it states that any regulus function can be extended to a regulus function on an ambient smooth set. Okay, so now a theorem which I don't know whether it is published somewhere, but it is kind of theorem which is well, everybody working in this area is more or less clear. So this theorem makes a bridge between this first historical part and the new part. So consider smooth real algebraic set, function f is regulus if there exists a pi which is from x prime to x, which is the composite of finite sequence of blow-ups with smooth Zariski cloud centers, such that f composed with pi on x prime is a regular function. So one could say that a regulus function on smooth subsets, one could call them also blow regular, in the same way as Kuon did it. So in particular, you see that regulus functions on smooth sets are arc-analytic and semi-algebraic. And this is a point where we change with Wojciech. We'll continue.
Krzysztof just recalled two characterizations of regulus functions. However, there are other interesting characterizations, and we need to introduce some definitions to explain what's going on. So the setting is we take a real algebraic set X in Rn, and we take a function f defined on a subset W of X. And the definition has two parts. We say that the function f is curve regulus if for every irreducible algebraic curve C in X, the restriction of f to the intersection of W and C is a regulus function. This defining condition is equivalent, or means precisely, the following. The restriction of f to the intersection of f of W and C is continuous and has a rational representation. It is convenient to introduce also a localized version of this definition. That is the second distinguished part of this definition. We say that f is arc-regulus if for every irreducible algebraic curve C in X and every point X in the intersection of W and C, there exists an open neighborhood U sub X in W of the point X, such that the restriction of f to the intersection of this neighborhood U sub X and C is regulus. Once again, it simply means that this restriction of f is continuous and has a rational representation. It is clear that any curve regulus function is arc-regulus, and probably you need a moment of reflection to realize that the converse does not hold. So I'm not going to spend time on giving an example. Okay, with this preparation, we are ready to give the first characterization, well, the third characterization of regulus functions. This characterization was obtained in a joint paper with Janos Kolar. The paper was published in 2017. The assumptions are X is a real algebraic set, W is a subset of X, which is assumed to be either open or semi-algebraic, and then a function f defined on W is regulus if and only if it is curve regulus. So the theorem says that we can decide whether or not a function is regulus just by looking at the restrictions of the function to algebraic curves. One implication is, of course, trivial here. If f is regulus, then it is curve regulus, so the issue is to show the reversed implication. We also have a result which corresponds to the notion of arc-regulus, and the appropriate formulation is as follows. Let X, as before, be a real algebraic set, W a subset of X, which this time is assumed to be connected, smooth, and open. Smooth means simply that W is contained in the non-singular locus of X. Under these assumptions, a function f defined on W is regulus if and only if it is arc-regulus. So once again, we can decide about whether or not the function is regulus just by looking at the behavior on algebraic arcs. There are two main parts in the proofs of these two theorems. In the first part, we assume that W is an open, connected, smooth, and semi-algebraic subset of X. And in addition to that, we also assume that f is a semi-algebraic function. So this is the semi-algebraic case of the theorems. And then, in this case, the main role is played by the classical Bertini theorem. The main difficulties, however, are concentrated in the second step of the proof, which is the reduction of the general case to the semi-algebraic case. In this reduction, we use a delicate theorem from analysis. We don't know a purely algebraic geometric proof, and this analytic theorem is due to Błodzki and Siciak. It is well known that Hartog's theorem on separately holomorphic functions does not hold in the real case. Nevertheless, Błodzki and Siciak proved some Hartog's-like theorems for real analytic functions, and we use one of these theorems to reduce the general case to the semi-algebraic case. I would like to give one more comment about the proof. Namely, if we assume in the first theorem, say, that the function is arc-regulus, then we have to show in particular that the function f is continuous. But even this is not obvious, and in fact we do not know a simple direct proof of this fact. Of course, it is a true statement because we are proving much more that the function is regulus, but we don't know a simple proof that the function is continuous. So let's move on to another topic. In real algebraic geometry, we usually study objects which are defined by real polynomial functions. However, in the last few years, a new branch of real algebraic geometry somehow emerged, and in this new branch, that I will call regulus geometry, we study objects defined by regulus functions or K-regulus functions. So let me introduce now K-regulus functions. let U be an arbitrary open subset of Rn in the Euclidean topology. We say that the function defined on U is K-regulus if it is, first of all, regulus and of class Ck. Here K is any non-negative integer. If we take the set curly Rk of U of all K-regulus functions on U, we obtain a ring. An example of a K-regulus function is provided here. It is f sub k, given as a quotient of two polynomial functions. Of course, it is understood that we extend this definition by 0 through the origin. So this function already appeared in the first part of the talk. A basic property of the ring of K-regulus functions on U is that it is contained in the ring that Krzysztof introduced, namely the ring of semi-algebraic Arc-analytic functions. And similarly, like in this Arc-analytic case, the ring curly R K of U is not Noetherian if n is greater than or equal to 2. It makes perfect sense to talk about regulus functions which are of class infinity. However, when we do that, we don't obtain anything new because any C-infinity function that is regulus is automatically regular, and therefore, for this reason, from now on, I will restrict this discussion to K-finite. When we study regulus geometry, it is convenient to introduce a new topology on Rn. Let us recall first that a subset A of Rn is said to be constructible if it belongs to the Boolean algebra generated by algebraic subsets of Rn. In other words, A is constructible if and only if it is the finite union of Zariski locally closed subsets of Rn. So how do we get a new topology on Rn? It turns out that if we take all sets which are Euclidean closed and constructible, then this family of subsets of Rn is a family of closed sets of a certain topology called the constructible topology on Rn or C topology on Rn. So on Rn, we have considered several topologies already. The relationship between them is indicated below. The Zariski topology is contained in the constructible topology, which in turn is contained in the AR topology that Krzysztof talked about. And Krzysztof also mentioned that the AR topology is in fact contained in the Euclidean topology. All these inclusions are strict inclusions except some trivial cases. Subsets of Rn which are closed in the constructible topology can be characterized in a very nice way. This characterization comes from a paper of Fichu, Huisman, Mangold, and Monnier. The paper was published in 2015. For a subset E of Rn, the following conditions are equivalent. First, E is exactly the zero set of some ideal I of the ring of K-regulus functions on Rn. 2, E is the zero set of a single function, which is K-regulus on Rn. And 3, E is closed in the constructible topology. So, constructively closed sets can be described using K-regulus functions. And by the way, Krzysztof mentioned that I will explain the name K-regulus. Well, the explanation is simple because these four people introduced the name. And of course, there is no such word in the English language. So the term is derived from two words, regular and continuous. I already mentioned one algebraic property of the ring of K-regulus functions, namely, this ring is not Noetherian if the dimension of the space on which we consider the functions is greater than or equal to 2. So it is definitely a negative statement. However, it turns out that the ring of K-regulus functions on Rn has some remarkable properties. The most important property is the Nullstellensatz, which was proved once again by the same 4 mathematicians in the same paper of 2015. The theorem says that if we take an ideal I of the ring of K-regulus functions on Rn and a K-regulus function f on Rn which vanishes on the 0 set of the ideal I, then a certain positive power of f belongs to the ideal I. So as you see, the formulation here is exactly like the formulation of the classical Nullstellensatz for the ring of polynomials over the complex numbers or over any algebraically closed field. Here is a little illustration of this theorem. If you take the ideal I generated by this very simple function g, if you take h given by the formula, then the 0 set of the ideal is just the origin. However, the indicated power of h is in the ideal, since the function f sub k that we already saw at least 2 times is K-regulus on Rn. So when you look once again at this example, you see that the Nullstellensatz does not hold for the ring of real polynomials or for the ring of regulus functions on Rn. So that is because the Nullstellensatz does not hold in these 2 cases. It is very nice that it holds for the ring of K-regulus functions. The fact that we have the Nullstellensatz for K-regulus functions is very important for the development of sheaf theory, or at least basic sheaf theory. So let's consider an assignment, or rather, first, let's consider Rn endowed with the constructible topology. So the topology is fixed. And now we consider the assignment curly Rk. To each open set U, we assign curly Rk of U, the ring of K-regulus functions on U. This defines a sheaf of rings on Rn, and sheaves of Rk modules on Rn are called K-regulus sheaves. It follows from the Nullstellensatz that I discussed a moment ago that in the context of K-regulus sheaves, we have classical formulations of Cartan's theorems A and B. More precisely, the following theorem holds. If F is a quasi-coherent K-regulus sheaf on Rn, then the first condition, F is generated by global sections, so that is frequently called Cartan's theorem A. And the second condition, the cohomology group H upper I of F is equal to 0, provided that I is greater than or equal to 1. So as you see, these Cartan's theorems A and B have exactly the same formulation as in the complex analysis on Stein spaces or in algebraic geometry of affine schemes. So why is this theorem of interest in real algebraic geometry? The explanation is simple. Because Cartan's theorems A and B fail for coherent algebraic sheaves on Rn, and it has been known for at least 40 years that they do fail in this situation. So it is quite nice that we have in the real case good formulation of basic properties of quasi-coherent sheaves. We pass to another topic. I will talk now about approximation, some approximation results in the real algebraic geometry. To provide some background, I will talk about some historical facts. Conjecture 1 that you see was around already in the late 70s and early 80s of the last century. If X is a compact real algebraic set, then the conjecture says that for a continuous map F from X into the standard unit sphere SP, the following conditions are equivalent. Condition 1, F can be approximated by regular maps. Approximation means approximation in the compact open topology. So in simple language, uniform approximation in this case. And condition 2, F is homotopic to a regular map. Of course, condition 1 implies trivially condition 2, so the issue is to show that 2 implies 1. Around the same time, about 40 years ago, or no, exactly a lot earlier, there was another conjecture, conjecture 2. It is about maps between unit spheres. For any pair NP of positive integers, each continuous map from Sn into Sp can be approximated by regular maps. Despite considerable effort, and despite the fact that people looked at these conjectures for many years, very little is known in general. It seems that there is only one non-trivial general result, and that is covered by an old theorem of Bochnak and myself that we published in '87. This theorem says that conjectures 1 and 2 hold if P is equal to 1, 2, and 4. Why these special values? I will not go into the discussion of this because time is limited. You could also wonder whether in conjecture 1 you could say that for any x, any continuous map from x into Sp is homotopic to a regular map or can be approximated by regular maps. In general, this is not the case, and for example, there is this result of Bochnak and myself that we got in '93, a continuous map from the standard unit torus S1 to the power n into S2 can be approximated by regular maps if and only if it is null homotopic. So only exceptional maps can be approximated by regular maps. So what happens in the new context? The explanation is contained in 2 papers of mine that I published in 2009 and 2014. Let X be a compact, smooth, real algebraic set if F is a continuous map from X into Sp, and if we assume this stuff in red, that the dimension of X is equal to P, then the following 2 conditions hold. I'm not saying that they are equivalent, they hold. F is homotopic to a K-regulus map for any integer K greater than or equal to 0. And condition 2, F can be approximated by regulus maps. In general, this theorem does not hold if the dimension of X is greater than P. My papers contain explanation what happens in this case, but it would be too long to go into details. And the same 2 papers contain an answer. So I wanted to mention a result about maps between spheres. If you take a continuous map from Sn into Sp, then 1, F is homotopic to a K-regulus map for any integer K greater than or equal to 0, and 2, F can be approximated by regulus maps. So as you see, this, we have reasonable results if we deal with regulus maps, and the situation is pretty much open if we are interested in approximation and homotopy properties of regular maps. So now the very last topic that I want to discuss, vector bundles on real algebraic sets. People consider usually R vector bundles, C vector bundles, and H vector bundles, where H stands for quaternions. And the following question attracted a lot of attention. Which topological F vector bundles on a given real algebraic set X admit an algebraic structure? There is a classical result of Fossum and Swan. If you consider vector bundles, can I have 2 minutes? 1, okay. So, as you see the statement of the result, and there was a conjecture that you could replace Sn by an arbitrary compact non-singular real algebraic set, but that is not possible, and that is the content of the next theorem. So the very last slide, a theorem from a new paper of Krzysztof and myself. If we take regulus vector bundles, which are defined exactly like algebraic vector bundles, but with the help of regulus functions, then on any compact real algebraic set homeomorphic to Sn, each topological F vector bundle admits an algebraic regulus structure. I will skip the last theorem and go to the very last slide. Thank you very much for your attention.
Thank you for this interesting talk. Questions for them?
Can you replace the global approach for semi-algebraic by local approach for semi-analytic or sub-analytic?
But what type of results would you like to get in such a general context?
I don't know. I don't know.
Analytic functions are in fact blow-analytic, so that you can resolve singularities by blowing up global centers. So maybe this, in this sense, but it may go. But I think in some situation one can repeat this theory.
Well, the theories actually already exists in the case that you consider an analog of regulus functions in the Nash context. You can take the quotient of two Nash functions and say that it is Nash regulus if it is, has a continuous extension. And then pretty much everything what I explained goes without a lot of changes in that context. So that is a mixture of an analytic context and this algebraic context.
Not purely analytic. Nash is between the two cases, algebraic and analytic.
Analytic without any extra assumptions, or?
Maybe this meromorphic kind of
Meromorphic, well,
yes, it makes sense.
Meromorphic analytic functions, then there would be some technical difficulties. Maybe in a compact case on compact analytic manifolds, certain things would go through, but I'm not positive at this point.
Have you thought about equisingularity of sets in the context of regulus functions?
Not yet, unfortunately, so that would be a nice next project. Unless, Krzysztof, have you thought about it?
It is more complicated than one can expect. What we have seen from this solution of linear equations. So Yes, if you want to obtain kind of stratification by this C-constructible function sets, no, yes, no, this is a problem in general. So, to continue, so analogy complex and regulus is limited somehow. I think.
No more questions? Okay, so we thank the speakers again. Thank you.